This is why the HTTP won't work for the Internet of Things. This talk's kind of formed out of my own personal experiences working for a company that does IoT. I know it's a pretty new concept to a lot of people here, so we'll talk a little bit about that. But I just kind of wanted to make a disclaimer first of all. Yes, I do work for a company that provides IoT services. I don't think this talk will affect our performance either way. I think we still earn money whether you guys use HTTP or not. So just want to keep it neutral here. So this is really just generated out of my own personal experiences with working with IoT. So let's just get started. So first of all, about me, I'm a software engineer. I cut my teeth as a web developer. So I'm really familiar with HTTP. I've used it a lot. I've used it for enterprise application integration. Currently, I do distributed systems, so we use HTTP on the back ends too sometimes. But it really doesn't work for the Internet of Things. And so this is kind of, I'm going to try to show you this over the course of a couple slides and then show you some solutions that do work. A little bit more about me. When I design software and software systems, I prefer systems that are simple. Because when you make them simple, it scales a lot better in a lot of ways. It scales for when you're adding servers, scales up for more traffic, it's usually more performant systems, and it also is easier to understand, easier to bring new people on. Simple is always better. So if we can take the simple route, it'll win every single time. And HTTP worked exceptionally well for the web. I'm not trying to argue that. HTTP made the web successful, but the web is not the same problem as the Internet of Things. All right, so the Internet of Things. This diagram kind of shows it. So you take an embedded device and put it on the Internet, and you have IoT. So an embedded device, that's a single-purpose device. So your cell phone isn't actually an embedded device. It's more of a general-purpose computer. So you can do pretty much anything you want on it. An embedded device would be like the basketballs we have out in the IoT zone out there, something that just measures some sensor values and publishes it somewhere. We work with a lot of trucking companies and shipping companies. There's a lot of applications there. So we've been doing embedded for a long time, and we've been doing the Internet for a long time. But when you put the two together, a lot of things happen. Like for instance, embedded devices are really fun and nice. You can do a lot of cool things with them, but they're even more fun if you can have them talk to each other. They're even more fun. You can do so much more if you can publish that data to the Internet and gather analytics and that sort of thing. The Internet is also a great thing. Facebook, Twitter, it's enhanced. Think about Amazon. You can buy anything and have it shipped to your house in a day or two. So the Internet is an amazing thing too, but then when you add devices to that, you can start having the computers sense the world around you and make intelligent decisions. So there's a lot to be gained by putting these two things together, but there's also problems with each of them. Like embedded engineers face totally different problems that web developers face. But when you put the two together, both problem sets are still there. In fact, you have even more problem sets, and they almost compound. So I would say the value of each of these things are compounded when you put them together, but also the problems are also compounded. So you take two things that are already big topics and you put them together and you have a really big topic. So there's a lot to be talked about. We can go on for days about this, but I don't think I could last that long up here. But yeah, so this is kind of the introduction to the Internet of Things. As far as embedded devices, I'm assuming most people here aren't really embedded developers. I'm guessing that because I don't see a lot of neckbeards, but maybe just hid those well. So embedded devices typically are constrained. Constrained by memory, constrained by processing power, and especially constrained by networking capabilities. So to break that down a little bit, memory-wise, an embedded device frequently only has 2 to 4K or kilobytes of memory. That's on the low end. Usually they're more like 20, 40, maybe 100K. But you compare that to your laptop, like I have a Mac running this thing, that has like 8 gigabytes of memory. That's magnitudes more. It's totally different problems. And so we're talking about memory. We're talking about that's room for the operating system, that's room for the program's instruction set, and also that's room for the actual stack and heap and what's actually running the program, what the program's actually consuming. So all that has to fit into 20K, 10K, 4K of memory. That's a totally different problem. Something we're not normally used to dealing with, especially as like a web developer. It's totally different. Interestingly, when you're using MCUs, an MCU is an abbreviation for a microcontroller unit. Basically just a CPU stuck on a board with sensors and whatnot. When you're in that situation, frequently you'll have either an embedded operating system like embedded Linux or Kentucky, but a lot of times you have no operating system. That means the device boots up and it starts executing the first instruction of the main function of the C program, and it just runs to the end, right? So it's a little bit different. Actually, it's a lot different. There's no threading. There's no contention with their processes. So some things are simpler, and a lot of things are a lot harder with embedded engineering. That reliable network connectivity thing, that's also really important. So sometimes you do have a reliable internet connection. Sometimes you can actually just plug right into the wall. Sometimes you could plug right into the wall, but it'd be a lot more convenient if you could just plug into, say, like a power socket and communicate through the power lines. So power line communication, that's the thing. People actually do that, and sometimes it's really useful. Also, you might have to be on a wireless network. Sometimes you can use Wi-Fi. Wi-Fi is pretty good. It's pretty reliable, but it sucks a lot of power. Generally, the longer the bandwidth or the wavelength, the more power it's going to consume. So the longer the signal travels, the more power it's going to consume. So Wi-Fi consumes a lot of power. GSM and CDMA, the cell phone networks, they're going to consume even more power. General rule of thumb, you can probably get around that. But then shorter wavelength or shorter distances like Zigbee and some of those mesh networks, those are going to consume a lot less power. So we're generally for IoT, we're going to stick to shorter wavelength things, maybe mesh networks and whatnot. Yeah, let's move on. All right, so just to kind of visualize this is kind of what some IoT devices would look like. So the big one right here, that's a Raspberry Pi. Has anybody seen a Raspberry Pi, held it, played with it? They're kind of fun, actually, because they're actually more of a general-purpose computer. It has a full Linux distribution on it. But there's the pins on the upper right-hand corner of the Raspberry Pi. So you can integrate with sensors pretty easily. But you can also program in Python and whatnot, so it's pretty easy to work with. Way up on the upper right-hand corner, the two fingers, the guy's holding some sort of microprocessor there. That's more typical for what we're talking about. That sort of thing will probably let a battery last for days, weeks, years. Sometimes these embedded devices have batteries that last for a whole decade or even multiple decades. That can be that might be a requirement. Sometimes you have a power source. You can use energy harvesters. Sometimes you just have to make best use of your battery and make sure the battery lasts for a really long time. As far as power harvesters go, energy harvesters, you can use solar panels, but there's problems with you have to maintain solar panels, and they're sometimes finicky. Or windmills, whatnot, or actually better yet, like maybe motion sensors. Not motion sensors, but you can actually generate motion energy off of the motion in the body. My brother, he actually has a really cool energy harvester that he did his master's thesis on that generates energy based on the change in heat throughout the day. So in the morning, as the day is heating up, it generates energy. And as the day cools off at the end of the day, it also generates more energy. So it's a pretty cool technology. It uses an alloy called nitinol. So just things like that, you take those things into account. So I hope at this point you've probably been convinced that this is a different problem than the web, different problem than JavaScript in the browser. It's really not the same thing. It can be on that level, but a lot of times it's not. Also, side note, if you remember Commodore 64, I'm actually kind of young. I didn't really use Commodore 64. I actually thought 64 stood for 64-bit wide processor. And that actually stands for 64K of memory, which is not much. I mean, I think a single web page runs more than that a lot of times. But yeah, also Texas Instruments, or TI, Qualcomm, and also Arrow. Those are some logos you might look at for devices. All of them sell sensors, also microprocessors. An actuator. Actuator is a term that's used for an output. So a sensor would be an input, actuator would be an output, something that does something. We're talking more about telemetry data. So there's several avenues you can take with IoT. Home automation, industry automation, enterprise automation, those sorts of things do happen. But we're talking more about telemetry here. Telemetry data is just sending sensor readings from sensors to usually a server or the cloud. It's usually where it's going. I mean, you can have instances where sensor readings go from device to device, but generally we're talking about reading sensors and then publishing them out to the cloud somewhere. That's pretty typical use case. Seems like that's what everyone wants to do these days. When you're doing this telemetry data, you end up with a lot of data. I mean, you have to think about how many devices are out there. If you listen to Gartner and all those forecasters, they're talking about like billions and trillions of devices out there. It's kind of seems like made up numbers, but when you think about it, we've talked about web scale, like what Twitter and Facebook do. They have millions of users. Now imagine millions of users, but each user has maybe 10 devices on their self or under their purview, maybe 100, sometimes 500 devices, and multiply that by the millions, and you started talking about scales of devices growing up a lot. Like, that's how you get to those millions, billions, sometimes trillions of devices. It gets, it compounds pretty quickly. When we do telemetry data, we found that publish-subscribe model works very well. If you're not familiar with publish-subscribe model, or PubSub, it's generally your typical internet chat room. If you've never used an internet chat room, Twitter and Facebook, they're pretty much the same thing. So you have a data producer, which would be sensors in this case, that publishes data to a broker. And the broker distributes messages, reroutes them to whoever needs to get them. So the subscribers don't get messages that they're not interested in, and they get all the messages that they are interested in. So the broker is kind of that single point that just routes everything, right? So in this case, like I mentioned before, we have sensors publishing to devices. That's definitely happens. Usually in that case, the data is never leaving this room. It's going to stay all in one general small locality. More commonly, like I was saying before, we're going to publish to the cloud, and this is where Salesforce comes in. This is where you're going to be publishing lots of data and consuming it into Salesforce, maybe condensing it first and then pushing it into Salesforce, so you're not just filling Salesforce with tons of data. There's also other connectors too. I assume you're mostly interested in Salesforce though, so there's that. Okay, HTTP, again, it doesn't really work for what we've talked about so far. First of all, it's a text-based protocol. Being a text-based protocol, it has quite a bit of overhead. So you think about an HTTP request, and you have a bunch of headers at the beginning, and then you have the body of the request. Now, of course, the protocol doesn't really specify what's in the body. We don't really care. We just want to send data. So we're looking at what's the overhead on top of the HTTP request, and those are the headers. How big are the headers? I was talking to some experts, and they're just kind of shooting out numbers. Obviously, the lower bound of how much data, how much overhead HTTP has is pretty small. I'd say it's probably, I don't know, like 50 bytes or something like that. That's bare minimum, but nobody writes HTTP headers that are that small. Usually, we're talking about 100K. That's kind of on the large side, maybe more like 10K, but it's quite a bit. But if you think about that, think about like a typical request being like 2K, which is okay, about fair, about average. That would probably blow the entire memory quota for the device. You just fill up the entire device and it just shut down and it wouldn't even be able to send the HTTP request. Maybe you don't have devices that are that small. Maybe you have larger devices, but still you have those the networking requirements. Like sometimes you have a reliable network and sometimes you don't. And what if there's a high packet loss? What if the packet doesn't send the first time, so you have to resend it? If you're sending a lot of data, you have to resend a lot of data over and over again until it finally succeeds. So you might want to shoot for smaller messages, so you have to resend less messages. Also, some networks like Zigbee, they have constraints about how big a message size can be. In Zigbee, it's really small. It's like, I don't think it's even 100 bytes for that matter. It's really small. So we have protocols specifically for Zigbee to work correctly. So Zigbee is a mesh network, which means each node in the network always routes messages. And so you can expand the network by just being, you can participate in the network by being close to another node. And if that node is close to another node, then you can reach further and further and further. That's kind of the idea behind mesh networks. So HTTP, I'm sure you're all familiar with this. I'm assuming that's why you're here. Or you make a request to a server, usually a resource, and the server processes the request and sends the response back. So it's a request-response pattern. That pattern works exceptionally well for the web. However, when you're talking about telemetry data, like we've been talking about, I think telemetry data is what we're talking about when we're talking about the Internet of Things. This is generally what it is. This doesn't really work very well. One of the reasons is devices, the clients, they're small again. They have to handle the errors. And when you have to think about how many errors there are. With HTTP, you have client errors, you have server-side errors, you have protocol errors, you have I don't know what wrong errors, like the 700 errors or whatever, 600 errors. There's all kinds of errors to handle, and you have to handle them in different ways. And sometimes you might want to resend, and sometimes you don't. That makes things kind of complicated. So it makes things more complex on the client side. Again, we want simple systems. If we can make them more simple, it's better. This is especially important on these clients because remember, we're talking about that device cardinality thing. How many devices? I might have 200 devices under my purview, on my body or my car, on my phone, whatever, my house. When you have that many devices, it becomes difficult to, say, deploy updates to your software. So if maybe you forgot to handle a corner case, maybe you forgot to handle a certain error a certain way, you might have to redeploy a patch. And that's hard, especially when you scale that up to, say, like millions or billions of devices. Redeploying a patch is not a simple task. And yeah, there's definitely ways to deploy patches, but if we can avoid that problem, that's going to be great, right? It's going to keep our systems more simple and all the advantages of being simple, right? OK, again, so HTTP. So the consumer would be the server. So in this case, you'd be sending an HTTP post or a put to the server to send sensor readings and whatnot. That means the server has to be available at all times. And when the server is processing the data, that could mean that there's it's a pretty complex web app there to process the data, maybe do some machine learning or whatever you're doing. You're probably going to have to redeploy the software on the server a few times just to adapt to changes and whatnot. So making it completely available all the time might not be an easy chore. Of course, we have ways to go around that, and so there's always that option. So it's not a killer point right there, but it's something to consider. Also, the publisher needs to know the exact destination. That means a host name. And what if you have this service going and you love the service and it's operating perfectly, but then you have this new idea, and so you want to try another service. How are you going to make 15 million devices published to 2 places instead of 1. First of all, that's 2 sets of traffic. You're doubling the traffic. And then B, you have to configure 15 million devices. That's kind of a hard problem again. Again, we're trying to keep things as simple as possible. So if you're going to keep things simple, this might not work. So MQTT stands for Message Queuing Telemetry Transport. If you want more information, there's also MQTT.org. Also, if you use the Eclipse IDE at all, iot.eclipse.org also has more information about it. Anyway, it's an open spec. It's a pub/sub protocol, so we tend to prefer it. It's also a compact binary protocol. So we're talking about the overhead involved with HTTP. Well, MQTT only has 2 bytes of overhead, only 2 bytes. That's practically nothing. OK, again, so it's a pub/sub protocol, so the broker has to be available at all times, which it's pretty easy to deal with since the broker only changes whenever a new version of the protocol spec is updated. Also, at Telemetry, we actually horizontally scale our broker so that it's never actually not available. There's always one node that's up to take traffic. So we can do that with MQTT also. Also, yeah, that's good enough. Oh, I think the most important point, I think I've mentioned this before, is with PubSub architecture, is the data producer or the sensors is insulated from errors that happen on the server side, in the cloud or wherever. So again, we have complex logic in the cloud, and we have to redeploy it frequently, and it's going to fail every now and then for whatever reason. And the publisher doesn't have to worry about that. All it has to worry about is publishing to the broker. It just sends data to the broker, and the broker receives it and does things with it. And if the internet connection is out, then it just waits until the internet connection is back up, and then just sends more data. So it's about as simple as it can possibly be. So this is why I like PubSub, and I especially like MQTT for PubSub for Internet of Things devices, just because it simplifies the program down to as simple as it can possibly be. MQTT offers a feature called QoS, or Quality of Service. The protocol, on the wire protocol, they're numbered 0, 1, and 2. Generally, they're called, like 0 is called at most once, or some people just call it fire and forget, which sounds scary. Really, all it is MQTT runs on top of TCP, so it has all the same guarantees as TCP. So if both sides are up and available, then the message will arrive. If one side is down, it won't arrive, right? Then you have QoS 1 and 2, which have higher guarantees than TCP. So if one side is down, it'll just synchronize at some point. And at some point when they're both up, they'll make sure the message is delivered. This is a really critical thing for IoT because we don't have reliable networks. And so we have to ensure that the network will be reliable enough. How much time am I taking? OK. Just a side note, QoS 1 is a lot easier to scale. If you're familiar with distributed systems, this might make sense for why at least once delivery is easier to scale than exactly once. There's ordering issues, the cap theorem and whatnot. There's some reasons for that. But you can always implement QoS 2 using QoS 1 on the client side, and it's actually really easy to scale. It just makes the clients a little bit more complex. So if you can get away with QoS 1 or even QoS 0, then always go simpler if possible. But general rule of thumb, you can actually fabricate QoS 2 out of QoS 1. MQTT has topics. Well, actually, pretty much every PubSub system has topics. However, MQTT has hierarchical topics you can pattern match on. So you don't have to publish to the exact same topic. So a topic is kind of like an address. If you're in an internet chat room, the chat room would be the topic, right? So you publish to a topic, and when you subscribe to a topic, in MQTT you can subscribe to whole patterns. So the pound would match anything from the pound to the end, and so only the first part of the topic would have to match. And the plus sign only matches just one segment of it. So because of these dynamic topics, as I call them, one of the design patterns we follow is to put a lot of metadata inside of the topic itself. So you might put device IDs in the topic. You might put some information about the actual content of the message. Like you might put the content type, like it's JSON. So let's put JSON in the topic name. And we can subscribe to only the JSON form or just the XML form or just the protobuf form or whatever. Also, two more features. So last will and testament is this feature so that when the device unexpectedly goes offline, you can have it prearranged to just send out a message. And also retain messages so that when you send a subscribe request, the broker will automatically push the value that was last published on that topic. So you can use retain messages to kind of implement that RESTful architecture. And together, last will and testament and retain messages, you can actually implement a roll call system so that just the simple broker system, you can actually implement like full applications or simple applications, like keeping a roll call, for instance. So just to keep a full directory of who's online and some metadata about them. So it's kind of a cool little thing. MQTT-SN is a sister protocol to MQTT. So it's for sensor networks, so like Zigbee. It's meant for mesh networks, but it really works on any datagram-based network. Datagram like UDP or text messages, that's also a datagram. You could probably implement it over email if you wanted, but I don't know how you'd do that. So probably the most, okay, so also you're probably seeing that term there, 6LoWPAN. That'd be mesh networks. It's IP version 6 over mesh networks, essentially. So a lot of the really small embedded devices are concerned with that. The main feature, the selling point of MQTT-SN is this gateway. So when the gateway comes online, so it translates MQTT-SN messages into MQTT. And when it comes online, it has does a UDP broadcast. So it just broadcasts to everyone that, oh, look, I'm a gateway. I can handle your MQTT-SN messages. And the same thing when a client comes online, it searches for gateways. And so you have this configuration-free discovery. So this makes the idea of having hundreds or thousands of devices under my purview, it makes it a lot easier to handle that kind of situation when you have this configuration-free discovery aspect to MQTT-SN. So again, this is kind of the architecture of an MQTT-SN network. So you just pop a gateway onto a mesh network, and it translates. The gateway would have to span both a mesh network and an actual TCP network to handle the MQTT traffic. But it bridges both protocols, and so you can send really low-level, like maybe body area network data, like about your muscles or about your movements. You can send that to the cloud. Okay, so I'm going to talk briefly about CoAP. So CoAP is it's also a RESTful architecture like HTTP. So say you've been listening to this presentation and you're like, okay, this works, this is great and everything, but I'm actually doing IoT applications, but I'm not actually doing telemetry data. I'm actually doing some command and control stuff. And HTTP really does make sense to me. CoAP is exactly like HTTP, but only lighter. It runs on top of UDP, so you have that 6LoWPAN thing going for you. It has mappings in the protocol spec. It has mappings to the HTTP protocol. So it supports the four main methods, get, post, put, and delete. And it's a really compact binary protocol. I think it only takes like 3 or 3.5 bytes of overhead. It's kind of interesting it can take half a byte, but it does. So it runs over UDP. And so most of the time, you're going to have unreliable transfer, which is totally fine for most cases that are on Zigbee or the mesh networks. But every now and then, you're going to need to have reliable transfer. So we have an option set called confirmable messages. So you can make sure, it's kind of like TCP, implementing TCP on top of UDP. The cool thing about CoAP is the protocol specifies the resend intervals. And since it does that, there's been some researchers have been able to make devices that consume 99% less power because they only turn the wireless radio on for a really small percentage of the time, like less than 1%. So that's kind of a cool little tidbit about that. This is probably my favorite feature. So it has an observe option. So you can make a GET request and set this observe option. And so the GET request gets the current value of the resource, right? But then sometimes the resource changes. And what this means is that when the resource changes, the server will automatically push a second or third or fourth message to you. And so it's server push, right? Which HTTP doesn't have that. I think HTTP 2.0 does have that. I know HTML5 has a WebSockets spec or aspect to the spec to implement server push, and so you can kind of use that to do it. But that's, of course, we're talking about really hot, heavyweight stuff at that point. So if you want to be on this level, it's kind of a nice little feature. There's a new spec that's being created in IETF right now for CoAP MQ. You can implement a message queue on top of CoAP also. And so maybe if you like MQTT, but you do mostly request-response pattern, you can just use CoAP and do mostly request-response pattern, but then use CoAP MQ for that message queue. So it can be a really convenient little tool in your toolbox. So this presentation is pretty much over, but here's some resources. So first of all, the IoT zone. There's a lot of stuff going on over there. You can go in, do some labs, and get your hands on some hardware. We've got that basketball court going, connected basketballs, kind of fun little demonstration. As far as CoAP and MQTT, I mentioned a couple URLs, iot.eclipse.org. Eclipse is really heavily involved in MQTT. They've taken under their umbrella a lot of the open source clients and open source tools. They've enhanced the Eclipse IDE to really provide a lot of value, really set you up for success for IoT projects. App.thingfabric.com, that's our product. We provide a lot of services on top of MQTT and top of, we have a multi-protocol broker. So you can publish MQTT and subscribe on some other pub/sub system or push to Salesforce or whatever. And then I mentioned previously my brother's power harvester, energy harvester. So there's a link for that if you're interested in that sort of thing. But with that, I don't know if we have a microphone. We can pass around a mic for some questions. Excellent, yeah. So I guess the system is if you have a question, just stand up and ask it, right?
Yep. So is it working? I'll just talk loud. Oh, there, now I hear it going. So talk some about security. So for example, Facebook Messenger uses MQTT. Mm-hmm. I don't want my Facebook messages going anywhere. Is that all above the app level, or are there any, I mean, above the protocol level, are there any standards emerging for how to do security over MQTT or anything like that?
That's an excellent question. I would say there is no winning strategy yet that everyone's generally accepted. I think it's generally accepted that you're going to do end-to-end security. So you're going to encrypt the message on the client side, and the subscribing client is going to know how to decrypt that message. That's generally how they're going to do it. I know if you've heard of the All-Scene Alliance or AllJoin, that's how they're starting to use MQTT for some of their web traffic going outside of the local zone. And that's how they're doing it. They're doing end-to-end security, so encrypting it on both ends. But even still, yeah, there's definitely some security concerns, like that first or second slide where you have embedded technology plus the internet. It's the same thing. It's like you take the problems of both and they just compound. So security becomes, yeah, like a horror story when you're talking about IoT. It's true. But there's definitely a lot of ways around it. I could point you to like a whole bunch of research papers about different methods of encryption that would work better for IoT. What was that?
Handcrafting is the answer. Do it however you want. Make sure you're secure.
I don't think handcrafting is particularly the answer. I think it's better to use tools that are pre-built by experts.
Oh, no, but what I mean is you grab whatever tools that you think are good and put them together yourself.
Oh, yeah. I think there might not be a general solution that works across the board. But yeah. Next question.
So we've been using RabbitMQ the past couple of months in a project in our organization. We've noticed that we haven't had fantastic throw pits in real-world use cases. I was wondering if you could speak to maybe some statistics on throughputs in MQTT.
So could you elaborate the question?
So basically, when we've run load tests, we've maybe got like 5,000 or 10,000 messages per second, which is decent for some applications. But I was wondering maybe if, off the top of your head, you could speak to some of that from MQTT.
Right. Yeah. That's a great question. Personally, our broker, we've been able to pump out 250,000 messages per second. We just stopped because we didn't have the resources to continue. MQTT wasn't designed to be, okay, so there are some corner cases that it doesn't scale well with. If you have a subscriber that's consuming all the traffic, it doesn't do particularly well with that. I think RabbitMQ's protocol, AMQP, does better. Kafka does especially well for consuming large amounts of traffic. So that's why we've built a multi-protocol broker, because MQTT does really well receiving traffic from embedded devices, but it doesn't do so well in that server-to-server communication land. So if you have that multi-protocol broker, you can accept, you can use a protocol where it makes sense and another protocol where it makes sense in a different situation. So we might use MQTT to accept traffic and then Kafka to push it between servers. and then HTTP to push it into different APIs like Salesforce and whatnot. But yeah, there's definitely some scaling issues, but even still, you can make it scale pretty far.
Does MQTT work with all the message brokers like TIBCO, MQ series, or is it just for Kafka? Does it support the protocol? Like, typically most of the brokers, they support HTTP, but I'm new to MQTT, so I just wanted to understand that, like, all traditional web brokers, like, whether it's an ESB tool,
Right.
In the market commercially available ESB tools like WebMethods or MuleSoft, or do they support MQTT?
So I'm not sure if I understand your question. MQTT isn't software, it's a specification. Okay. So it's one of the protocols, and you can make it somewhat compatible with, say, AMQP or JMS or something else. But by default, there's some incompatibilities there. So there's at least one reference implementation of MQTT, and there's a lot of other implementations, both on the broker and the client. You can find implementation on just about any client, library, language, platform, what you want. But MQTT itself is not software, it's just a specification.
Thank you.
Okay. Any more questions? If you ever, if a question pops up later on, you can, so there's my Twitter handle, you can use that. You can always just walk over to the IoT zone. There's a lot going on over there, a lot of people. I've been hanging out there all day. I'll be there for the next 3 days or whatever until Thursday. So yeah, with that we can shut this down and go on to the next fun activity.